Use logarithmic differentiation to differentiate the function with respect to x. We have the function y equals 3x to the fourth minus 2, all raised to the fifth power, over 3x cubed plus 4, all squared. So we want to use logarithmic differentiation. We're going to take the log of both sides first. I'm going to do natural log on the left and natural log on the right. We have 3x to the fourth minus 2 to the fifth over 3x cubed plus 4. Then now that we have that natural log in the equation, we now are able to use log properties to rewrite this equation. We can write this as natural log of 3x to the fourth minus 2 minus natural log of 3x cubed plus 4 squared. Excuse me, I left the 5 off here. So that was the quotient rule for logarithms, and we can also use the power rule for logarithms and write this as natural log of y equals 5 natural log of 3x to the fourth minus 2 minus 2 natural log of 3x cubed plus 4. Now this is going to be a much easier format to calculate the derivative than the original format. In the original format, you have to use the quotient rule because of the fraction and the chain rule because of having an expression other than x inside the powers. Whereas here, we just have to use our natural log derivative rule. So we're going to calculate the derivative on the left with respect to x. So we've got the derivative with respect to x of natural log y, and the derivative with respect to x of the whole right-hand side, 5 natural log of 3x to the fourth minus 2 minus 2 natural log of 3x cubed plus 4. So on the left-hand side, we have a mismatch of variables. So we are going to calculate the derivative, but we have to consider the chain rule. So this becomes y prime over y. On the right-hand side, our variables do match, and so we'll just use our normal derivative rule. So that would give us 5 times the derivative of 3x to the fourth minus 2, that would be 12x cubed, over 3x to the fourth minus 2, minus 2 times the derivative of 3x to the third plus 4. That would be 9x squared over the 3x squared plus 4. And let's see. This gives y prime over y equals 60x cubed over 3x to the fourth minus 2 minus 18x squared over 3x squared plus 4. And then we would solve for y prime by multiplying by y on both sides. And remember, y is what was given in the original equation. So we're able to substitute in for y this original equation here. So it's going to be 3x to the fourth minus 2 to the fifth over 3x squared plus 4 squared times what we have on the right hand side here. So I'm doing y times all of that, 60x cubed over 3x to the fourth minus 2 minus 18x squared over 3x squared plus 4. And this is our derivative, which is acceptable. We can do a little bit more simplification, and it'll cause some canceling out. And the reason why it causes some canceling out or combining is that you can see here this denominator of 3x to the fourth minus 2 is the same as this factor over here. And this denominator, 3x squared plus 4, is the same as this factor right here. So if we were to take the time to combine these two fractions together into a single fraction, we would be able to do some combining and canceling with these factors over here. So let's take a moment to do that, although this is acceptable as the derivative. So if I were to get a common denominator, that would be 60x cubed times the other denominator, 3x squared plus 4, minus 18x squared times the other denominator, 3x to the fourth minus 2, all over our common denominator of 3x to the fourth minus 2 times 3x squared plus 4. So with this now being a multiple instead of a term, I can cancel out one of these, and I'm going to be able to combine these two together to now become a 3 instead of a 2. So this is the derivative, it's 3x to the fourth minus 2 to the fourth over 3x squared plus 4 cubed, and I just need to clean up the inside with the distributive property and combining like terms. So that would be 180x to the fifth plus 240x cubed minus, let's see, 18 times 3 is 54x to the sixth minus, that would be a plus 36x squared. Let's see if we have any like terms we can combine in there. So we do not. So let's write this as let's see, actually we have a common factor we could cancel out. All of these terms have x's, so we could factor out an x. And all of these terms are even, so we definitely have common factors, but I want to get the highest common factor between them. So between 180, 240, 54, 36, let's see, I know that 9 is not going to work. Let's see, 6 goes into all of them. Let's try that for now, and then I can go bigger if I need to. So I'm going to factor out a 6x squared. If I factor out a 6x squared, that would give me 30x cubed and 40x. 6 into 54 goes 9 times, so that'd be 9x to the fourth. And then 6 into that would go 6x. No x there. So now I can move this 6x squared to be with this other group. So 6x squared times 3x to the fourth minus 2 to the fourth over 3x squared plus 4 cubed. And let's write that in descending order. We would have negative 9x to the fourth plus 30x cubed plus 40x plus 6. Okay, I'm going to zoom out so we can see the whole thing. On this example, we want to use logarithmic differentiation to differentiate the function with respect to x. So we're going to use logarithmic differentiation by taking the log of both sides. And we have to be a little bit careful with this one because we have this exponent here, which is only attached to the x. So we need to expand our logarithm before we can apply the power rule. So that would give us natural log of 2 plus natural log of x to the 2x. So this step here uses the product rule for logarithms to expand. And then once we have it so that the exponent is only on that x term, we can use the power rule for logarithms. So that would give 2x natural log of x. Now that we've expanded it, we're going to use implicit differentiation to calculate the derivative. So we calculate the derivative on the left, calculate the derivative on the right, and on the left our variables don't match, so we get y prime over y. On the right, the derivative of natural log 2, that's the derivative of a constant, that's going to be 0. And then on the second term here, we need to use the product rule to calculate the derivative. So we'll do the first times the derivative of the second plus the second times the derivative of the first. A little bit of cleanup before we go further. Y prime over y, those x's cancel out, so we get 2 plus 2 natural log x. And then we're going to multiply both sides by y. Remember that y was given to us in the beginning of this problem. So y is equal to 2x to the 2x, 2x to the 2x, times 2 plus 2 natural log x. And we can go one step further. In this parentheses, we have a common factor of 2. If we factor that out, we can multiply it by the 2 that's outside the parentheses to become 4. And then inside, we're left with 1 plus natural log x. So we've got the derivative of y equals 2x to the 2x to be 4x to the 2x times 1 plus natural log x. In this example, we want to find the derivative of f of x equals e to the x over x plus 5. And we're going to find the derivative using the quotient rule because we have a fraction here. So with the quotient rule, I'm going to write out the rule for you. The pattern that we follow is for calculating the derivative of a fraction, f over g. And we're going to do g times f prime minus f times g prime over g squared. So that's the denominator, excuse me, I've lost my mouse here. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So in this example, our numerator is e to the x, and our denominator is x plus 5. So let's find that derivative with the quotient rule. So we've got the denominator of x plus 5 times the derivative of the numerator. The derivative of e to the x is e to the x, minus the numerator is e to the x times the derivative of the denominator. The derivative of x plus 5 is 1 over that denominator squared. So that's over x plus 5 squared. I'm going to clean this up just a little bit. What I notice is that I have a common factor in the numerator. I can factor out that e to the x, and I'll be left with x plus 5 minus 1. And we can simplify that to be e to the x times x plus 4 over x plus 5 squared. So that gives us the derivative of e to the x over x plus 5 being e to the x times x plus 4 over x plus 5 squared. On this example, we're going to be evaluating the definite integral. That's the integral from 0 to 3 of e to the 3x dx. So I'm going to show you two different approaches for this. I'll show you an approach with pattern recognition and then an approach with substitution. So the first thing we need to do is to find the antiderivative of our argument here, the e to the 3x. But because our exponent is 3x, we need to consider the chain rule with this example. So the derivative of 3x is 3. So in order to make our antiderivative rule work, we need a 3 over 3. And we're going to pull in the 3 that we need. So we'll write this as 1/3 the integral of 0 to 3 of 3e to the 3x dx. So now we're going to be able to use our antiderivative rule for e to find the antiderivative. So that rule that we're using is the integral of e to the u du is e to the u plus c. Well, so the part that I've done where I've put the 3 over 3 and pulled the 3 in is because we have a u in the exponent and we need to have the derivative of that inside the integral before we can apply the rule. Now that we have that, we can apply the rule, and that gives us 1/3 e to the 3x. And this is a definite integral with bounds, so I'm not going to put the plus c. We're going to do the bounds from 0 to 3. So using the fundamental theorem of calculus, we would get 1/3 e to the 3 times 3 minus 1/3 e to the 3 times 0. That's 1/3 e to the 9th minus 1/3. E to the 0 is 1. We have 1/3 e to the 9th minus 1/3. So that's the integral with pattern recognition. If we're going to do this problem with substitution, it would go a little bit different. So I have the integral of 0 to 3 e to the 3x dx. And on the side, I'm going to let u equal 3x. The derivative of u with respect to x is 3. I'll rearrange those, multiplying by dx on both sides, and then dividing both sides by 3 would give me du over 3 is dx. So this information gives me my substitution. I'm going to substitute in for 3x to become u. I'm going to substitute in for dx to become du over 3. But I need to also change these bounds. These bounds are for x, and because I'm changing to u, I need to change those bounds to u's. So for x equals 0, u would equal 3 times 0, which is 0. And for x equals 3, u would equal 3 times 3, which is 9. So I'm going to change those bounds to 0 to 9. So all of those substitutions gives me the integral of 0 to 9 of e to the u du. Oops, sorry. E to the u du over 3. That 3 is a constant multiple, and I have 1/3 the integral of 0 to 9 e to the u du. I'll find my antiderivative. That's e to the u. We're going to use the fundamental theorem of calculus. And that's big F of b minus big F of a. 1/3 e to the 9th minus 1/3 e to the u. And that simplifies to be 1/3 e to the 9th minus 1/3, because e to the 0 is 1. Thank you for checking out my videos. Have a great day.